Hi everyone. Alright, this may be one of the last lessons we have for these videos. May have a review video before our last test, but we're talking about steps for graphing y equals a times b to the x minus h plus k. You have that in your notes. I did kind of add to it a little bit. Notes from the previous day. I'm going to talk about sometimes a is negative, so I put an absolute value. So if you graph it with a being positive times b to the power of x, if you graph that with a table of values, if a is negative, then if it's positive, you just leave it where it is. If it's negative, you're going to reflect those values over the x-axis. And then, after you reflect that, you translate the graph h units right and k units up. So do the translation after that. I'm going to change this problem around just a little bit. I'm going to change this to y equals 4/5 to the power of x. That would make things fit a little better. And the domain and range, we'll talk about those after we look at the graph. But first thing we're going to do is I'm going to graph the parent function, and this is exponential decay, so we need to talk a little bit about what happens there. Here's my x, here's my y, and y in this case we're taking 4/5 to the power of x. So let's go from -3, -2, -1, 0, 1, 2, and 3. And 4 divided by 5 is 0.8. So we're going to take 0.8 to the -3rd power, 0.8 to the -2nd, and so on. So I'm going to take 0.8 to the power of -3. I get 1.95. And I might, just to work with it a little bit, figure out what -4 is also, but we'll say that if we need it. 0.8 to the power of -2 is 1.5625. I'm just going to go 1.56 to the nearest hundredth, just like I did on there. 0.8 to the power of -1 is 1.25. 0.8 to the 0 power is 1. 0.8 to the first power is 0.8. 0.8 to the second power is 0.64. 0.8 times 0.8. 0.8 to the third power is 0.512. Okay, so it's not going down very much. I do think I want to put a few more values in here. I would like to look at x and y here at -5 and -4 also. So 0.8 to the power, not divide, 0.8 to the power of -5 is 3.05, and to the power of -4, 0.8 to the power of -4 is 2.44. Okay, so let me go ahead and plot that one, and let's see what exponential decay is looking like here. -1, 2, 3, 4, 5. 1, 2, just a slight bit over 3. -4, 2.44. -3, 1.95. We're going down a little bit below -2 there. -2, 1.56, about halfway between 1 and 2 there. -1, 1.25, quarter of the way down. 0, 1, right on it. 1.8, 2.64. So it is kind of curving down. 3 point is 3 is halfway down. Like that, I think. So, and then it kind of just continues to go down slowly toward the x-axis there. And then it'll actually, eventually, I'm wondering what, 0.8 to the power of -6. 3.8, so it's almost a 4 there. Okay, but I think it looks kind of like that. Now, that's what that one is. The domain is all values of x will work. For x, I should say. The domain's -infinity to infinity. The range is, it does not go, this is an asymptote, the x-axis, so it does not go below 0, it doesn't go to 0. So we use the curved bracket, 0 to infinity. So, let's look at graphing this one. On the last one, the idea is still the same, but I did add this -2 into it. So if I were to double all these values here, so like this one would be 6.1. So at -1, 2, 3, 4, 5, I'd be at 6.1, 4, 5, 6, a little bit over 6. I can change colors on that one. So I'm going to go blue here. And then 2.44, if I double that, that's 4.88. So I'm just doubling all these. Maybe I should, and I'll put it in the table when I get to here. This is the 2 times 4/5 x. So, and then I'll put 1, 2, 3, 4, and then that's 4.88, like right around there. And then, let's see, double this, 1.95. I think that if you double that, that's almost 2/4. So that's about 3.9. 1, 2, 3, 1, right around there. 1.56, that's 3.12, I think, when you double that. At -2, 3.12. And -1, you're at 2.5. -1. Okay, I messed up there, it looks like. This is 2.12, so let's go 3.12 right here. That point's errantly drawn. 2.5 is right here. I double 1, I get 2, so I'm right there. This is 1.6. This is 1.28. Okay. This will be a little higher. 1.28. And this is right at 1 when you get here. So, if I reflect all these here, I'm right around 6. I'm going to use a pencil for the reflection. So this is kind of y equals 2 times 2/5 to the x. So I'm going to reflect all these, and that's right around 6. So it's be -6 here. 3, 4, 5, just right there. A little bit below 5, a little bit above. 1, 2, 3, 4, 5. A little bit above -5. 1, 2, 3, 4, 5. So a little bit above. And then 1, 2, 3, a little bit below. 1, 2, 3, and almost -4. 3, right around there. -2.5. -2. There. I'm starting to see it. Okay. So this is the graph of the reflection of this one. Reflected this one after it multiplied by 2. Now that's multiplying it by -2 just to reflect that. And now let's move those 1 unit right and 2 units down. Move this one 1 unit right and 2 units down. I run out of room, so I'll do this one 1 unit right and 2 units down right at the bottom of the page. This one 1 unit right, 2 units down. Okay, let me do this one in blue. Move this one 1 unit right, 2 units down. This one 1 unit right, 2 units down. This one 1 unit right, 2 units down. 1 unit right, 2 units down. This one 1 unit right, 2 units down. This one 1 unit right, 2 units down, and then it will keep going like that. So we're going, this is the graph that we're trying to approach here, right here. So what did we do? Well, this was already there. We went ahead and multiplied it by 2 and graphed that. Then we reflected this, and then we translated 1 unit right and 2 units down and got this one. So when we talk about domain of this one, I still think we're going negative infinity to infinity. X can be whatever, but the range. Okay, now we have a top limit, and that top limit is -2. That is as high as it gets. Now it gets, you can go as low as you want with it, but the highest it will get is -2, but it won't ever quite be -2. It'll always be a little bit under -2. So there we go, guys, and that's graphing exponential decay. Now when we flip it, it looks like it's exponential growth, but it's just the opposite there of exponential decay.